Okay, I think we can start now. Today, we are very happy to have King Van Tilburg, a joint assistant professor at NYU and Flatiron Institute. And he will tell us about stellar basins of the gravitational bound particles. You can start now. I will turn off my video.
Okay. Thank you, Da, and thanks for the invitation, albeit virtually, having me back. So today I will talk about work that I've been doing since February, but wrote up in June in this preprint here. And since then I've done a follow-up with a postdoc at Stanford, Robert Lazenby. So the first paper was a paper about, it included a case study about axions, and in the follow-up paper, we worked out many more of the details, and in particular the case of dark photons. So the basic idea is that stars, including the sun, are known to be able to emit weakly coupled particles like standard model ones, such as neutrinos, but also beyond the standard model particles, such as axions. And the basic idea is that non-relativistic axions or other particles can actually dominate the energy density at late times. So in sort of form a halo around the star, which I call a stellar basin or a solar basin in the case of the sun. Okay. So to give you the one slide summary, so as I said before, the sun doesn't just emit photons or any of the other stars, but it can also emit neutrinos and other weakly coupled particles. And these other alternative emission processes can actually dominate the energy loss of the star. So, and the reason is because the photons have such a high optical depth that the mean free path is so short that it's only a surface layer on the outer surface that's emitting or losing energy. And furthermore, that surface is much colder. It's 6,000 Kelvin, which is much colder than the core, which is 15 million Kelvin. And so just thermal Bremsstrahlung neutrinos can dominate the energy loss of certain stars, including these more extreme stars here. So neutron stars and white dwarfs in particular. So our sun is an ordinary main sequence star with 1 solar luminosity and 6,000 Kelvin surface temperature. Yeah, and so neutrinos are the remnants of more extreme stars, and the first 100,000 years of a neutron star's life, neutrinos form the dominant cooling mechanism of these stars. And so the same is true for non-standard model particles, including axions. So stars, including the sun, can set effective constraints on axions from not observing anomalous cooling processes. So there's various population studies you can do based on luminosity functions or pulsation rates of certain stars to constrain axion couplings. Furthermore, you can also try to look for axions for solar axions directly. So ones that are produced in the sun and then potentially absorbed in a detector, let's say one in Italy. Yeah. So a second way that these detectors can look for axions is just if they're primordially around. So if they're part or all of the dark matter, then the abundance is fixed, and then or assumed, and then you attempt to look for absorption, for example. And what I did was basically say if you have a coupling of axions, regardless of whether they're the dark matter or not, as I said, they can be produced in the sun. Most of the particles will be relativistic, but some small fraction of the phase space will be non-relativistic, and an even smaller fraction of the phase space will actually be emitted into bound orbits. And it's a tiny fraction of the instantaneous luminosity or energy loss to axions. But the bound population accumulates over a long time and forms what I call a stellar basin. And so, what I'll show for the rest of the talk, I'll describe how they can come to dominate the local energy density. So the bound population can exceed the unbound population of axions, and also for dark photons, it turns out. So that's the one slide summary, in case there's any questions. So feel free to interrupt at any time. I don't mind at all. Actually, I like it. So to give you a quick summary of for which particles it could be relevant, the short answer is every single one, but it's sort of useful to classify them into these 10 leading operators in effective field theory. So if you have a light bosonic particle that can be produced in stars, it can be a scalar, a pseudoscalar, or a vector. Those are your options. So spin 0, parity even, parity odd, or spin 1. And then the relevant couplings are those to electrons, quarks, photons, and gluons for a scalar and a pseudoscalar. And then for vectors, there's further constraints. If you want the U1 symmetry to be anomaly free, so you can have the dark vector A prime can be a kinetically mixed photon with a kinetic mixing epsilon with R massless photon. Or it could couple to a baryon minus lepton number. And so in my first preprint, I worked out the case of axions coupled to electrons, for which the dominant processes of axion emission are Bremsstrahlung and Compton production. So where you Brem an axion off an electron, or you have photoproduction of axions off of electrons. If you have the photon coupling, you can produce axions through the famous Primakov process, and that can also lead to photon decays. But just for simplicity, I'll first show just a single coupling to electrons, and I'll assume there's no anomaly with photons, so it's just a dimension 7 operator that's generating the leading decay of photons. So that. But I mean, the photon coupling could be present, and I'm just for simplicity ignoring it. And so I'll discuss this case in the first half of the talk, and in the second half of the talk, or the last part of the talk, since many things are the same, I'll go through the same exercise for kinetically mixed hidden photons. So the processes are the same. It's still Bremsstrahlung and Compton production. Now the decay is automatically slow because it's effectively a dimension 8 operator. That's always for all couplings exceedingly small. There are differences though with Axion, which is that production can occur resonantly. So the relative production in the sun versus that in more extreme stars like horizontal branch stars or red giant stars is enhanced relative to the case of the Axion. So these are the different couplings and processes. Any questions so far? All right, again, feel free to interrupt at any time. So let's talk about the axion. So just have the kinetic term, axion with the mass m, and this coupling to electrons that I quantify with this coupling GAEE. And in the plot on the left here, I plotted the axion mass versus axion coupling to electron parameter space. And from not observing anomalous cooling of the cores of red giant stars or of white dwarf populations, you set constraints that are on the order of 4 and 3 times 10 to the minus 13 respectively. The solar constraint is about an order of magnitude worse, just because for these two processes, the dominant emission process is bremsstrahlung, which goes like density squared, and the core of a red giant and a white dwarf are much denser than the sun. That's why they set better constraints. And there's some hint of anomalous cooling of white dwarfs, but I wouldn't take that too seriously. If you do, the best fit region is roughly in this salmon colored band.
Sorry, can I just ask a question? Can you remind me, I think it's something I should know, but why aren't supernova a stronger constraint? They have higher temperatures, right?
Yeah, they have much higher temperatures, but they also have much higher output also of neutrinos. So the neutrino rate scales like a faster power of temperature than Axions does. I think 2 extra powers of temperature, and the same powers of density, I believe.
Okay, all right, thanks.
Yeah, I'm not sure what constraint you get. So the supernova constraint on this very same coupling, but then to neutrons and protons, gives you 10 to the in FA gives you 10 to the 8 GeV, and if you translate this to a decay constant, you get 10 to the 10 GeV. So
I think, I'm sorry, I think I was thinking about the coupling to nucleons, where I think you do get the strongest constraint from supernova.
Yeah, yes, to nucleons you do get the strongest.
I just forgot you were talking about electrons.
Yeah.
Okay.
Yeah, indeed. But even if you say that the coupling to protons and neutrons is the same, this will be the leading constraint. So the supernova one would be subleading.
Really? Okay.
Yeah.
Okay.
Yeah.
All right,
so if you translate this to an effective FA, if you just write this coupling as just a mass in the denominator, you get about 10 to the 10 GeV. And the supernova, if you do it for the supernova constraint on the coupling to nucleons, you get 10 to the 8 GeV. So if you have a coupling to electrons, this is the leading constraint.
All right, thanks.
So these are the constraints from these more compact stars or stellar cores or stellar remnants. And I said this, the solar cooling constraint is worse. However, we can try to detect, because we live closer to the sun, we can try to detect the solar axion flux. And so in a paper by Redondo, he calculated the total solar spectrum. It's peaked at around a keV or so, which corresponds to the temperature of the solar core of 15 million Kelvin. And there's multiple contributions here. So FF means free. So that's basically the bremsstrahlung diagram that I had on the previous slide. Compton, which I also showed on the previous slide, is this dashed line here. There's additional contributions that I won't include in the rest of my talk, but will be additive contributions, and those are corrections or additional contributions from bound states, so atomic structures. You see there's a bunch of lines, and I'm assuming the Primakov contribution is negligible. I mean, which again, if you assume sort of typical couplings, it will be the case. Okay, but so this solar axion spectrum was for a massless axion. So what I realized was that, here I'm plotting again, so the differential, so Q is the energy loss rate. So if I plot the differential energy loss rate per unit energy as a function of energy for a typical star, if the axion were massless, you get some spectrum that rises because of phase space. And then for energies omega above the temperature of the core of the star, you would get Boltzmann suppression. So you get something that has this general shape. And this will be true for scalars as well. So the total energy loss rate is mostly relativistic, almost in all cases, even if the mass is heavy. However, a small fraction, basically, a blue strip here, will be emitted into bound orbits. And that fraction is just the area under the curve between energies just at threshold and where the kinetic energy is below that required to escape the gravitational potential under consideration. So just for reference, I forget the precise number now. I think the escape velocity in the core of the sun is 5 times 10 to the minus 3. So about a 10 to the minus 5. So if the kinetic energy is 10 to the minus 5, the rest mass energy, it remains bound to the solar system. So it's a tiny fraction of the luminosity, but it sticks around, right? So the unbound fraction just flies out of the solar system. And so to estimate what this fraction is, you can just consider any general process of standard model to standard model plus one Axion emission. And so to compute this, you have to integrate over all incoming particle momenta and integrate over all outgoing momenta, including the momentum of the Axion. So let me just write the energy loss rate as an integral over the Axion momentum, and then factor out everything else here in this Q tilde function. In general, if you have a matrix element that is not suppressed at low 3 momentum of the Axion, then this Q tilde integral is independent of the Axion momentum in the soft limit, in the limit that I care about. And then this D3K, this D3K integral here factorizes, and you just compute the fraction that's below the escape momentum, and you get mv cubed, mv escape cubed. Whereas generally, if you compute it for the total energy loss rate, you get something of order t cubed in general. So that's the twiddle. If you do it carefully, and this is what I show in my first preprint, then you can compute the energy density injection rate into bound orbits as measured at radius r, and this is the expression you find. So you find something that falls off as 1 over r to the 4th, and then it's a volume integral over the stellar interior of this Q tilde function, basically as defined here, times the square root of the depth of the gravitational potential, well, phi at that radius. Whereas the total energy, so the energy density from the unbound emission is just the total Axion luminosity, which is the volume integral of the energy loss rate divided by 4 pi r squared, just from Gauss's law. It's the luminosity over 4 pi r squared. And so as promised, the ratio of the bound energy density fraction over the unbound energy density fraction scales like v cubed, as I sort of argued heuristically there. It's v escape squared at radius r times v escape in the stellar interior. And then again, as I argued here, you get a factor of m cubed over t cubed from this phase space, and then another factor of m over t, because a non-relativistic particle has energy m and a relativistic one typically has energy t. So that's why you typically get a factor of m to the 4th over t to the 4th here. And then the remaining factor turns out to be, if you take this ratio the remaining factor turns out to be tau over r. So here I've assumed that the bound fraction is the injection rate, the integrated injection rate, and I'm assuming an effective total lifetime of tau. So you see here, so this factor of v cubed is tiny, right? Because the local escape velocity at Earth's position in the solar system is 30 kilometers per second, or 10 to the minus 4. So square that and you get 10 to the minus 8 times 10 to the minus 3 in the sun, and this red factor here is never larger than 10 to the minus 11. However, this fraction can be enormous. So this is the lifetime of bound orbits in the solar system divided by an AU, or 8 minutes. And if you work out this fraction, so at the optimal case of m of order t, you find that this ratio can be 1 if tau is 1,000,000 years at r of 1 AU. And as I'll argue, the effective lifetime, a conservative estimate of what the lifetime is, as limited just by gravitational ejection, is 10 to the 7 years. And that's, I mean, there's evidence that this is way too conservative, and very likely the actual lifetime is almost the age of the solar system for weakly interacting particles. So I don't have a very good idea. I mean, as you see, my estimates for this ejection lifetime span 2.5 orders of, or almost 3 orders of magnitude. So the 10 to the 7 years comes from very conservatively arguing that the chaotic timescale of the solar system dynamics is about 5,000,000 years. So, you know, you can conservatively say that after 2 Lyapunov times, so 2 chaotic timescales, particles are typically ejected. If you do a more, in my first preprint, I did a more careful estimate where I interpreted asteroid data and then simulations that people did of the fate of those asteroids to get at a lifetime of 100,000,000 years. However, that's probably still too conservative because asteroids are biased to be in the ecliptic plane and near mean motion resonances, so they're not representative of these particles that I inject here. And the most optimistic possible case is if the lifetime is just the age of the solar system. So if you just integrate over the full solar lifetime and you get 4.5 or 4.6 billion years. And I'm currently working on refining this estimate of tau, but in any case, it's much larger than 1,000,000 years. So therefore, if the mass of the axion is of order keV, then the local energy density will be dominated by the non-relativistic axion population, not the unbound flux. So that's the main point.
Can I ask a naive question?
Yeah.
I have the impression, maybe this impression is wrong, I have the impression that all the asteroids are far away. They're like outside of Pluto or something.
So
is that impression correct, first of all?
No, well, there's many asteroids in the Kuiper belt and the Oort cloud, many more than there are in the inner solar system.
Yeah.
When I say asteroid data here, I mean the asteroids from the asteroid belt between Mars and Jupiter, and in particular, not just those, but the ones that had semi-major axes close to that of Earth. So near Earth objects. And so most of them originated from the asteroid belt between Mars and Jupiter. And I mean, it's hard to know where they came from, but that's the most likely scenario. Some of them may have been comets from the outer solar system that were then captured via interactions with Jupiter, but those are thought to be a small fraction.
Yeah, so that's the other thing. Yeah, okay. All right, so it's not, anyway, you're not really relying on asteroid data very much, right? Because,
so, yeah, in the end, I mean, you know, these estimates, so there's no way to get an answer for tau unless you do a simulation.
Yeah.
And that's going to be well, not this slide, but the next one.
Okay.
So it turned out that a month after my paper came out, a friend of mine, Tim Weiser, and his grad students studied the case of a primordial solar dark matter halo. So they studied the case of the solar system forming in a dark matter over density and estimating how much of the bound density population survives. You know, so the initial conditions were slightly different from what I have, but they provided evidence that the gravitational ejection rate is indeed slow, so of order the age of the solar system. So 31% is about 1 over E, and you know, 31% is the amount of dark matter that survived the age of the solar system. And you see that, so this is a snapshot of the surviving phase space after this 4.6 gigayears. So Vx, positive Vx is velocity towards the sun, negative Vx is velocity away from the sun, Vy is the tangential velocity within the ecliptic plane, and Vz is the velocity, I guess this way, out of the ecliptic plane. And what they find is that these moderately eccentric orbits, these blobs here, and at moderate but non-zero inclination, did survive in the end, and you know, circular orbits did not, or at least they're driven out of this region into eccentric and moderately inclined orbits. They didn't exactly do full n-body simulations. They did. They used some phase-based diffusion tricks and some arguments about secular perturbation theory. But so they're motivated but not verified. So in a follow-up project I'm doing with incoming graduate student at NYU, Cara Giovanetti, and again, Robert Lazenby, we're doing n-body simulations, just gearing up to do them. But we have some preliminary evidence that indeed this gravitational ejection time is much longer than 10 to the 7 years. So this is a simulation of 100 particles run for 500,000 years, and we saw none of the initial parts. And they were indeed injected with conditions as expected from stellar emission from the sun. So initially the orbits are on very eccentric orbits, as you can see here. So this here is looking down on the solar system. The gray here is Jupiter's orbit. Mars, Earth, Venus, and Mercury is in the muck here. And these are 100 particles with an effective density profile like that of a stellar basin. And as you can see, spherically symmetric, at least on average. And so the semi-major axis didn't change over this preliminary simulation, the particles didn't get ejected, and the semi-major axis only changed a little bit. And it's not like it increases linearly in time. So it sort of librates around these values. And since this plot, we've run longer simulations, and it looks like the lifetime is larger than 10 to the 8 years. But at the moment, we're limited by computational time, and we're refining these things.
So I'm confused about one very basic thing, which is why don't these particles ejected from the sun fall back into the sun? I mean, if they were actually in elliptic orbits, they would. So are you assuming that there's enough of a perturbation that their eccentricity is reduced enough that they don't just end right back up in the sun?
So initially, indeed, they're emitted onto radial orbits, and they'll traverse the sun many, many times. But the optical depth is tiny, so they can traverse the sun many times before they get reabsorbed. Good. There is one exception for the dark photon that I'll talk about at the end of the talk. There is one part of parameter space where the occupation number can get so large in this restricted part of phase space, these really high eccentricity orbits, that you do get some reabsorption. Basically, at some point, you achieve detailed balance with the sun for some of these modes or for some of these parts of phase space, and then reabsorption kicks in, as well as stimulated emission. But just by detailed balance, you can show that there's a maximum occupation number you can grow to. For axions, it's never a worry. For the couplings under consideration, there's no reabsorption occurring. Okay, good. Yeah. It's actually also an interesting question. So because they traverse the sun many times, it's not exactly a Keplerian problem with the 1/r potential. So the orbits initially actually have order 1 perihelion precession per orbit, and that's one of the complications that we are facing. We need to modify existing codes to take that into account, and we don't know if that has an effect on the ejection lifetime. But so in the end, if you take my ridiculous range of parameters between the ultra-conservative tau of 10 million years, the optimistic tau of the edge of the solar system, and then the fiducial tau, which is what you get from Tim Weiser's paper, where they found a 30% reduction after the edge of the solar system, from which I got this number. You get the following situation. So for this fixed coupling, which is just barely allowed by the white dwarf cooling constraint, as a function of axion mass, you get a solar axion basin. So this is the energy density in these bound solar axions that's within this blue band. So the dashed line is the optimistic estimate, the thin solid line is the conservative one, and the fiducial one is close to the optimistic here. It's the thick solid line. And as you can see, it dominates the unbound axion energy density by at least a factor of 3 here, or 4 or 5, I forget precisely, up to a factor of 1,000. There's some small component from Bremsstrahlung from the Earth's core, but it's always subdominant. That's this green here. And just for comparison, I'm showing the dark matter energy density here, although for this population, I'm not assuming it is dark matter, right? It just can be dark matter. Are there any questions? Any more questions about this?
Sorry, sorry, can I just ask, what are these A, B, and C's? What are they?
Oh, sorry, I didn't explain. Yeah. So C is Compton scattering, B is Bremsstrahlung, and then that's in gold, and then the black is the sum. And then the green is Bremsstrahlung in the solar core. And so yeah, I didn't mention, but Redondo in 2013, when he wrote this paper, which is sort of the reference on calculating axion emission from the electron coupling in the sun, he called them ABC processes. The A are these atomic structure, atomic recombination and atomic structure processes that I have not yet included. So I've only included Compton and Bremsstrahlung.
Okay.
But actually, yeah. So there would likely be a factor of 1.5 increase here, just as there is for the unbound flux. Thank you. Sorry, I forgot to say. So to give you a brief summary of the xenon experiment, I think your audience knows already, but so the xenon experiment looks for dark matter scattering, but they're also sensitive to axion absorption. So the basic idea is that any scattering or absorption event can ionize electrons, and that gives you instantaneous scintillation light, as well as these ionized electrons that drift up in the electric field, and then give you after a drift time some additional scintillation light, allowing reconstruction in 3D. Within their fiducial volume, away from the walls of the detector where you have radioactive events, they saw an excess of events. So if you combine the S2 scintillation light and the S1 scintillation light, you can reconstruct the typical energy of an event, assuming it's electron fraction. And so this is what you get. So every black dot is an event they saw between 1 and 7 keV here. And if you plot it in 1D reconstructed energy, they saw an excess of events peaked at between 2 and 3 keV, which tantalizingly is close to the solar temperature. So they offered explanation. So very likely it's a radioactive background or some other unmodeled effect. It could be tritium or perhaps an argon line. They claimed, or at least they offered, an explanation of an unbound solar axion, which seemed to match the data, as I said. So this peak here at 2 keV is the same one that I showed from Redondo's paper. But if you plot the couplings that are required. So they turned on the ABC axion is the coupling to electrons. The red is from a Mossbauer decay from the nuclear coupling, and the purple is from the coupling to photons. If you plot what couplings are required in terms of the electron coupling, the photon coupling, and the nuclear coupling, the excess events are best fit by this blue banana here. But this entire blue banana is way excluded. So if the actual allowed region is this tiny corner here, which is compressed basically on the bottom plane here, because these couplings are way excluded by supernova cooling that Marcus asked earlier. So if I just compress everything onto the bottom plane here, one gets this coupling. So now the best fit, this parameter space, photon coupling and electron coupling. And the best fit parameter space is this red corner here. And the stellar cooling constraints, so the white dwarf cooling bound is what I said here, 3 times 10 to the minus 3. And then there's a horizontal branch cooling bound on the coupling to photons. So an unbound axion does not fit the data. So you could explain the excess events with dark matter absorption. So for example, the excess is fitted fine by a line between 2 and 3 keV. And for that, you need a coupling that's less than 10 to the minus 13. The Xenon collaboration did not plot the solar axion bound, the cooling constraint on this plot, which would be here. But the dark matter explanation fits it. And likewise for a dark photon. So dark matter, dark photon fits the excess. So we have 3 potential explanations. So this is a plot I made. Now, again, axion coupling to electrons as a function of axion mass. As I said, the excess is best fit with a coupling that's 3 times 10 to the minus 12, which is excluded by red giant cooling constraints and white dwarf cooling constraints. The line could be fit by their dark matter search. So all the dark matter searches are indicated by the dashed line. So for the S2 only analysis by Xenon, the S1 plus S2 analysis by Xenon, the one that came out over the summer, and then the experiments Panda X2 and Lux as well. So the dashed lines are dark matter experiments. And so my claim is that if the particle is not dark matter, but if the particle had a mass of order of keV, then you can reinterpret these dark matter searches, which are basically searches for axion absorption. You can reinterpret them in terms of the non-relativistic solar axions. And so because at a fixed coupling, the energy density of these non-relativistic axions is so much larger, you can set a better constraint by looking for this line absorption than looking for the broad spectrum relativistic flux coming from the sun. So that's the basic idea. So at a fixed coupling here, so at 3 times 10 to the minus 3, you get significantly more, you get significantly more non-relativistic energy density than you do relativistic energy density in axions.
Ken, sorry, I think I'm not getting the point of this, your big plot here.
Okay.
I mean, the dark blue line is your estimate of the signal, and it looks like it's excluded, but I just thought you told me it was fit by Xenon data, so
the relativistic axion explanation of trying to interpret it as an unbound axion flux,
right.
That is excluded, right, at 3 times 10 to the minus 12.
Right.
But what I'm saying is that, let's say the line is at 2 keV. So at 2 keV, I mean, it depends on tau. So if tau is if it's 10 to the 7 years, which is almost way too conservative, the density is not enough enhanced. So you can get away with a smaller coupling, but it would still be excluded by red giant constraints. If tau is close to, is a couple billion years, then the best fit coupling would be just at the border of this red giant cooling constraint. So I mean, it's marginal if you really want to interpret the excess. And
Okay.
there's strong reasons to believe that the actual I mean, I don't take it too seriously.
Okay, no, I got it. I just want to understand. So, but then what about all these other dark matter lines below? Are you saying that if that they should have seen a signal?
So if it's dark matter, right? So you could see solar axions. The particle could exist in the theory, but it doesn't necessarily need to make up all of the dark matter.
So those dashed lines would only be a constraint if this was also dark matter.
Yes, precisely.
Okay, I'm sorry.
Yeah.
Now I think I understand now. Thank you.
I mean, and if you want more details, there's actually reasons to believe that it should not be dark matter. Certainly the exclusions that they place above 10 or 20 keV are completely irrelevant, because you always have, no matter, even if you turn off the coupling to photons, if you say there's no anomaly with photons, right, which you can do, you just, it's some integer tuning, right, of the anomaly coefficient.
Yeah.
You can never tune away this coupling. So this is the dimension 7 operator. It's suppressed by the electron mass. So the electron threshold correction of this dimension 7 operator will lead necessarily to some decay to photons. That decay to photons is slow enough that you don't have to worry about depletion, but you do have to worry about X-ray constraints. So this would give you a line in the X-ray, in the extragalactic background, and above 20 keV, this would give you, this would be in excess of hard X-ray observations. So and below 10 or 20 keV, you really, for the case of dark matter, you really have to tune this. I mean, not tune. You have to set this coefficient to 0. Otherwise, you're also excluded even down to sub keV. And that's not the case for the stellar basin, because it's only, those axions are only near the sun, where there's a large thermal X-ray background from the corona. And that's something I'm investigating now with another graduate student at NYU, basically the indirect detection of this decay of axions close to the sun. But sorry, that's going off track. Yeah, so my basic conclusion is, just to summarize this, that liquid xenon experiments will essentially never be sensitive to the relativistic axion flux. It's only a factor of 10 in coupling, but it's a factor of 10 to the 4 in event rate. So unless they get 10 to the 4 times bigger, they will never be sensitive to the relativistic solar axions. My claim is now that, even if you don't believe the excess, my claim is now that in the region above 1 keV, so from, let's say, half a keV to 10 keV, they are now beginning to probe unconstrained parameter space via this solar axion basin, if tau is as large as I think it is. And they have been probing for quite some time now axion dark matter in the 0.2 to, well, in my opinion, 20 keV region, because here it's excluded by X-ray constraints. So that's the summary for axions. And I'll wait here for other questions if there are any. Otherwise, I'll move on to dark photons.
Maybe a very simple question. You are really focusing on the bosonic particle.
Mm-hmm.
What about the fermionic particle? Because there's a pressure?
Very good. So, well, that's something I'm thinking about as well. So basically, it's true for fermions as well. It's a bit harder because, of course, you cannot have single fermion emission for particles that are not neutrinos. So indeed, there is also a solar neutrino basin. Just from, let's say you have some fusion process with emission of a single neutrino. Some of the phase space, again, puts the neutrino just above threshold and into a bound orbit. But the occupation number can never get large. And so, you know, given the known neutrino masses, the energy density can never exceed what you get with occupation number 1. And we already know of a non-relativistic neutrino population with occupation number of order 1, basically thermal occupation number. And that's the cosmic neutrino background, and that's hopeless to see. So this solar neutrino basin will have an even lower density, because now you're restricted to bound orbits to the sun, not just to the thermal thermal energies. So
okay.
for neutrinos, it's small. The one potentially interesting case would be pair production of keV fermions coupled with some higher dimensional operator, let's say some effective new G Fermi of chi bar chi being the new fermions, coupled to E bar E with some gamma structure, spin structure. So that's a potentially interesting case. And I've started looking at this with Cristina Mondino, who's now starting a postdoc at Perimeter Institute, but we've not made significant progress since then, since we're both moving. But so my claim is this holds for any particle and any coupling. The one thing one has to keep in mind is that the matrix element for production should not be suppressed in the soft limit. So the basic argument that I made, that, for example, the bound density fraction goes like the escape velocity cubed, that's relying on the fact that there's no momentum suppression in the matrix element. So for some couplings, you might have momentum suppression, and in that case, basically this basin is irrelevant.
Okay, thank you.
Okay, so I'll move on to dark photons now. So the story is very similar, so it won't take that long. The one difference, but it's a major qualitative difference, is that you have plasma effects now and resonant production. So let's start with a normal Maxwell Lagrangian, and then there's also one for the dark photon A prime with a mass m squared. And now just a kinetic mixing between the field strengths here. And you can field redefine epsilon so that you have an effective gauge coupling of this new vector that goes like epsilon times E instead of just E. And if the dark photon mass is above the plasma frequency everywhere in the sun, for example, if the dark photon mass is a keV, then you get a very similar picture as to the axion. There's basically no qualitative difference. I mean, most of the energy loss rate occurs in the solar core, and then it's just steeply dropping here because both the density and the temperature in the sun fall off. However, if the mass of the dark photon is below 300 eV, which is roughly the highest plasma frequency in the core of the sun, you get this resonant emission, and that's because the dispersion relation of the photon changes. So that's one qualitative difference. The other qualitative difference is that, unlike the case of an axion, as the dark photon mass m goes to 0, there's no physical effects anymore from a dark photon. So this field redefinition that I talked about here basically can rotate away this epsilon to be a non-physical coupling in the limit of 0 dark photon mass. So So at low dark photon masses, any production of a dark photon is suppressed by positive powers of the dark photon mass. And in fact, for the longitudinal mode, m squared in the emission rate. So if I make the same plot, which is the resultant energy density of the dark photon basin as a function of dark photon mass, I get, for example, the blue band. So the blue band is where I assume a fixed epsilon of 10 to the minus 16. And then depending on tau, I get a range of predictions, but fiducially it's near this thick blue line. The dashed line is for the unbound energy density. So the total energy density of the escaping flux. And so you see that for masses above 20, in this case, 2 or 3 eV, the prediction is that the bound fraction dominates. So it's over a much wider mass range than for the axion that you get the bound fraction to be dominant. For the green band is where I set epsilon at the current limit before we put out our paper. So it turns out that we actually, even with the super conservative tau value of 10 to the 7 years, we actually improve the limit in the range of a few hundred keV. But before our paper, the prediction would be that you could even exceed the dark matter energy density in this range, but now because of our paper, that range is excluded. And in red here, I'm plotting the maximum density that you build up to because of saturation effects. So the red density is what you would get if you've reached thermal equilibrium. So if you've reached thermal detailed balance between spontaneous emission, stimulated emission, and reabsorption. So that lands you at a maximum value of the red curve. And indeed, you can actually achieve, so if epsilon is as large as currently allowed, you actually achieve this at low dark photon masses for a fully mixed phase space. And for the question I got earlier, so if the phase space is not fully mixed, but if the phase space diffusion from these very radial orbits to a fully mixed eccentricity phase space is slow, you may actually saturate to this lower saturation phase space density, and that's something we're investigating now. So conservatively, we should put the energy density here as the maximum. Okay. So this is the constraints plot that is not assuming dark matter for the dark photon. So in gray, I've plotted the previous constraints, the constraints previous to our paper. So I'll trace the curves now. So there's 4 curves. So this is the thin gray line here is a solar cooling constraint that sort of peaks at 300 eV, which is the plasma frequency in the core of the sun. There's a horizontal branch cooling constraint here, and that's it's you know, the resonant the most sensitive dark photon mass, or the most constrained dark photon mass, is an order of magnitude higher because of the higher density in the star, and then yet higher still is the red giant cooling constraint. And Xenon 1 ton looked for relativistic dark photons, and that set this thick gray constraint here. And so the combined of these 4 constraints is the gray region. And then if you interpret the line absorption dark matter searches, so but basically if you reinterpret the line absorption searches of Xenon 1 ton and Xenon 10 at low energies, you get for a very conservative gravitational ejection time of 10 to the 7 years, this blue region as your new constraint. And as promised, we set, even with this conservative tau, a better limit in the few hundred to almost a keV region for a dark photon. And if the fiducial value of a few times 10 to the 9 years is correct for tau, actually there's multiple new exclusion regions that appear. So this corner here, the big swath of parameter space here, another corner there, and a small chunk just above the ionization energy of xenon. And future experiments, for example, I'll just highlight here, super CDMS germanium. So their projected sensitivity reach is this for a solar basin. So extending it way down in energies. And here you can also see that all constraints decouple as the dark photon mass goes to 0. And indeed, if you believe the excess, that can also be fitted with basin population in this orange blob here at 1 and 2 sigma.
Ken, you know, your pointer is not showing up. When you say this line or that line, I can't see which one you're talking about.
Oh, sorry. So I apologize.
I just want to know about the last one you said, the super CDMS line. Is that the lowest sort of dashed line?
No, this here it'll be clearer. So,
okay.
So these are the dark matter searches, and there's a whole range of proposals for low threshold dark matter detectors that are now actively being developed. I sort of picked 3 representative ones. So there's semiconductor scintillators. I'm just plotting super CDMS germanium here. So this is their dark matter reach, this brown curve here between half an EV, and I mean, it goes all the way up to keV. So if you reinterpret this brown curve in terms of the constraint you could set on the dark photon basin, you get this blue region here, or in this blue line over here. Just recasting the sensitivity to dark matter in terms of this basin density, you get that, yeah. And then here I'm showing it, labeled as stacks, the dark matter sensitivity using layers of dielectric materials. So that's an experiment that I'm involved in together with Robert Lazenby, Masha Bari-Akhtar, and Junwoo Huang. And a prototype of this experiment has set a dark matter bound, or it'll appear soon, that's just poking out this constraint here. But the full eventual version should be able to achieve this dark matter sensitivity. And if you recast that in terms of a Axion dark photon basin coupling, it doesn't look too promising. I mean, so the bound fraction does decouple. So it's difficult to set better constraints at these really low masses. But super CDMS should be able to say something. And similar scintillators should be able to say something all the way down to 1 electron volt in mass. Yeah. And then, as I said before, so the excess can be interpreted by a dark photon basin, but it can also be a dark photon dark matter particle. But then you need to have a way of producing it in the early universe. I think I'm probably over time. No, just 1 minute left. Okay, good. So that's my conclusion slide here. So as I sort of briefly mentioned before, things that I'm still thinking about are basically indirect detection of this Axion basin from the decays around the sun, and we're also brainstorming conversion in the magnetic field around white dwarfs and neutron stars with Junwoo Huang and an incoming NYU student. I'm also investigating other couplings in particles. So I've shown you the case study for a hidden photon and an axion coupled to electrons, but one can consider CP even scalars as well as pair production of fermions, as Da asked. And I mean, probably the most critical question right now is to refine this gravitational ejection time. And so that's work that I'm doing with Cara Giovanetti and Robert Lazenby. And additionally, answering some questions related to reabsorption and saturation. And also, one thing I didn't mention during the talk is that eventually you would want to distinguish any tentative signal from a dark matter candidate or other types of backgrounds. So therefore, it's important to know the statistical properties of your signal as well as how it fluctuates in time. So unlike a dark matter, so this will have stronger annual modulation than a dark matter signal. So because we don't know this for sure yet until we simulate, but at least the way it's injected, the density falls off as 1 over r to the 4th. So Earth's eccentric orbit of a few percent should give you population annual modulation on the order of 13%, unlike the dark matter signal, which is only enhanced by gravitational focusing at the 1.5% level. And also the phases are different. So the signal here should be largest in January when the Earth is closest to the sun, whereas the gravitational focusing of dark matter is dominant in March and smallest 6 months later. In the end, obviously, one needs to do dedicated direct detection analyses. To 0th order, you can just reinterpret the standard dark matter searches or the standard line searches. But it would be nice to fold in the distinct temporal characteristics of the signal once we have that nailed down. And I've been in several discussions with LZ members and plan to as well with the other liquid xenon experiments or other future experiments that are coming online. Okay, I'll stop here and take more questions. Thanks again for inviting me.
Thank you very much.
Thanks.
I'm gonna give you applause. I think we have enough question. We can, okay, let's see if any other question. If there's no other question, we'll go to the discussion session.
Okay.
Okay, probably let's go to discussion section.